In this lesson, we're going to begin to make our steps towards learning about the newest model of the atom, which is the quantum model of the atom. We'll start by reviewing some basic principles from physics as we study light as a wave. Then we'll look at what Max Planck and Albert Einstein contributed to the study of light in relation to the atom. And then we're going to revisit Bohr's model and investigate some of the experimental studies he did with hydrogen and quantitatively look at some of the analysis he did in those experiments. We're then going to use that information to help us understand the flaws of Bohr's model, which will act as a springboard to the newest model, the quantum model. To begin, we've discussed the fact that light can act as a wave. And so when we're looking at light, we need to understand its wave-like properties. And as you know from your study of waves, waves has both a wavelength and a frequency. The wavelength, in which we use a symbol lambda to represent, and it's measured in nanometers, which are 1 nanometer is 1 times 10 to the negative 9 meters, is the distance between two crests or troughs of a wave. So when we're looking at the wavelength, it's this distance here. And as you can imagine with these waves, these values are going to be quite tiny, and that's why we use the unit nanometers in order to make these measurements. The frequency of a wave is the number of wave cycles that pass a point in a given unit of time. So if we're looking at this wave as it passes by, we can see how many times it will pass this particular point. So if you imagine dropping a rock into the water and the waves that it produces, you would look at one particular point and look at how many waves pass that point per unit of time. The symbol that we're going to use to represent frequency in chemistry is nu. It's kind of a fancy looking V to distinguish it from V velocity. In grade 10 science, you used F to represent frequency. And we're just going to be consistent with the textbook and use the symbol nu. It is measured in hertz, or a unit that will make more sense to us is seconds to the negative 1. And this is really 1 over second. So if we look at what frequency is, it's the number of times that it passes per second, and that's why it's 1 over s rather than being simply seconds. A formula that you learned in grade 10 science was the universal wave equation. And what it's going to do is relate the wave's speed, wavelength, and its frequency. Now, as you know, light travels at the speed of light, which is 3.0 times 10 to the 8 meters per second. We use the symbol c to represent the speed of light. Now, the speed of light is actually equal to the frequency of that light times its wavelength. And we can understand that a little bit further if we think about the fact that speed is the measure of distance over time. If we take the frequency of that light, if we look at the units here, it's going to be the number of cycles per second. If we times that by the wavelength, which is the length of the cycle, so it's meters per cycle, we can see that we're left with meters per second, which is the speed. So that's where this formula comes from. The speed of light is equal to the frequency times its wavelength. And this formula is more commonly used in this format, where frequency is the speed of light divided by the wavelength. So let's look at an example. We're going to look at some light that has a wavelength of 410 nanometers. At the moment, I don't want you to worry too much about this concept here of the spectrum of hydrogen. When you look back at your notes at the end of the unit, this will become more clear. So we have a line with light of 410 nanometers. So that's the wavelength of the light that we're dealing with, and we want to know its frequency. So we've got our universal wave equation, which is frequency is equal to c over lambda. And as you know, the speed of light is 3 times 10 to the 8 meters per second. Now what we need to do here with the wavelength is we need to convert it into meters. So we'll do that over here. We know that 1 nanometer is equal to 1 times 10 to the negative 9 meters. So therefore, if we have 410 nanometers, we can calculate our unknown of x. So what I've done here is set up a proportion, okay, with my known ratio of 1 nanometer for 1 times 10 to the negative 9 meters. And we need to solve for x here, which we'll do by simply cross-multiplying. So if we multiply 410 times 1 times 10 to the negative 9, we'll get this wavelength in meters, which is 4.1 times 10 to the negative 7. So this wavelength, now in meters, I can sub in here because my units are now consistent. And I can solve for the frequency. So the frequency here is 7.32 times 10 to the 14. And the units are 1 over seconds, or we can also write hertz. It's just really important if you are using hertz that you do understand that it is the unit of 1 over seconds, or cycles per second. So if we have light with a wavelength of 410 nanometers, its equivalent frequency is 7.32 times 10 to the 14. And that should give you an idea of how quickly these waves really are moving. That's a lot of cycles per second. Now let's look at the contributions of Max Planck and Albert Einstein to the study of light. Planck was trying to figure out why, when an object was heated, it gave off light. At the same time, Albert Einstein was trying to understand light that was being emitted in similar situations. Now, both of them ended up working with the exact same relationship. And that was that the energy of light is equal to a constant times the frequency of that light. And this idea came out of the fact that they both determined that light can only be emitted in tiny packets or in quanta of energy, meaning that there are only specific amounts of energy that can be emitted. Rather than there just being completely an infinite amount, there are only certain quantities of energy that can be emitted. That's where the word quantum is coming from. Now, Planck studied this, and then Albert Einstein confirmed this, and he looked at energy of light actually from the perspective of a particle. So these two ideas together suggested what is called the wave-particle duality of light. So Planck was thinking of light as being a wave, and Albert Einstein was thinking of light as being a particle. And the way that Albert Einstein described it is that he described these tiny packets as being photons. So when we say that energy was being released, we say that energy is being released as a photon. So this formula here is the energy of a photon, or one of those tiny packets of light. E is equal to h nu. H is Planck's constant, and it is 6.626 times 10 to the negative 34 joules seconds. So you can see when you look at this formula, if I take Planck's constant, which has the unit joules seconds, and I multiply that by the frequency of light, which is seconds to the negative 1, or 1 over s, you can see when I multiply these two values, I am left algebraically with joules, which is a unit of energy. Now this relationship makes the electromagnetic spectrum a little bit more clear. It gives the relationship between the energy, the wavelength, and the frequency of certain types of light. So you've seen the electromagnetic spectrum before. It organizes the different types of light from gamma rays to radio waves. And we have this small section from 400 nanometers to 700 nanometers, which we refer to as visible light, which is light that we can see. And it consists of the colors of the rainbow: red, orange, yellow, green, blue, purple. Now you can see here that the wavelengths of the light are listed above, and the frequency of this light is listed below. And let's make the connection between the energy of a photon in terms of its frequency and now in terms of its wavelength. As we can see from this formula, as the energy increases, so as E increases, the frequency increases. Or thinking about it the other way around, the higher the frequency of the light, the more energy there is in that light. If we sub in our universal wave equation, which is frequency is equal to c over lambda, if we sub that in for the nu here, we get a relationship of energy and wavelength. So energy is equal to Planck's constant times the speed of light divided by the wavelength. And what we can see here is that wavelength and energy are inversely proportional. So as the energy is increasing, the wavelength is actually decreasing. And you can think about this if you put some numbers in your calculator. Okay, when we've got a relationship like this, 1 over lambda, okay, as this number gets bigger, the energy is going to get smaller. And as this number gets smaller, this number will get bigger. Think of 1 over 1 versus 1 over 4, right? It's getting smaller as the wavelength increases. What this means is that shorter wavelengths have higher energy photons. So if we look back to our spectrum, when we look at the visible light spectrum, light with a wavelength of 400 nanometers, or purple light, is going to have more energy than red light at 700 nanometers because there's an inverse relationship. And we can see the same thing here. Wavelength, as we go from left to right, is increasing as the frequency is decreasing. And in terms of the electromagnetic spectrum, the energy is decreasing as we go from left to right because of this existing relationship. So let's look at an example. We're going to examine that same color of 410 nanometers. We want to know what color this line is and what is the energy of the photon. To identify what color it is, we need to look back at the electromagnetic spectrum and look at where 410 nanometers lie. 410 nanometers lies in the visible region, and it's in the purple or blue region. Being general like that is fine. You don't need to give an exact color. Okay, so the color of this light is likely violet or blue. So we'll say violet because it is close to the end there. To determine the energy of this line, we need to use our relationship E is equal to hc over lambda. H is Planck's constant, which is 6.626 times 10 to the negative 34. Joules second. The speed of light is 3 times 10 to the 8 meters per second. And our wavelength, we're using the same value from before. is 410 nanometers. But just like before, because our speed of light is in meters, we need to use the value in meters. So we've got 4.1 times 10 to the negative 7 meters. And when we plug this into our calculator, we get 4.85 times 10 to the negative 19 joules. Okay, so we now know all of the information about this band of light at 410 nanometers. We know its frequency from our previous calculation, and now we know the amount of energy that's associated with that light. Our next step is to move on to Bohr's theory and to look at the experiments that he conducted in which he applied Planck's and Einstein's theory of light. So first of all, just a very quick review of Bohr's planetary model. His model is that the nucleus of the atom is in the center, and the electrons fill the space in specific energy levels in circular orbits. So the electrons are essentially traveling around the nucleus like planets would around the sun. In the different energy levels, there's a different specified number of electrons. We can hold 2 in the first energy level, 8 in the second and the third, okay? And the fourth is a maximum of 18. Now what you're going to see when we look at the new model is that there are some flaws even with the number of electrons that we're designating to be the maximum. And we'll investigate that later. So if we look at a Bohr diagram, we'll just do nitrogen for now, okay? And you can do aluminum on your own as a second example. So we've already practiced and made sure that we understand how to count the protons, the electrons, and neutrons. And for nitrogen, it's got 7 protons, 7 neutrons, and 7 electrons. So to draw the Bohr model, we have our nucleus. How you represent the nucleus, if you want to represent it as a circle, that's okay. I tend to represent it as a box just to distinguish it from the first energy level. Sorry. Okay. On the first energy level here, it can hold 2 electrons. And on the second energy level, we've got 5 electrons remaining. So we're going to place them around. We put them singly first and then pair them up. So we've got a pair and then 3 single electrons. So this is the Bohr model for nitrogen. And you should do the same for aluminum as extra practice. Now, Bohr's experimental studies were with hydrogen. And this was one of the biggest flaws with his experiment, is that it applied beautifully to hydrogen, and the calculations that you'll see that he did applied beautifully to hydrogen or to 1 electron systems. But unfortunately, they did not apply to systems that had more than 1 electron. What he was working with was hydrogen in a gas discharge tube. So he put hydrogen into a tube and he applied a high voltage to it. When hydrogen was in this glass tube with the high voltage, it released this purple light. And what he did with that light is he allowed it to pass through a prism. When the light passed through the prism, what the prism did was it separated the light into the purple's fundamental colors. So this purple that we see isn't a fundamental color, but the prism diffracts it and it allows it to separate into its fundamental colors. So this purple light that you see is actually a blend of some red, some green, some blue, and some purple. The same thing would happen if we shone white light through a prism. If you shine white light through a prism, it's going to be separated into its fundamental colors. And when we're dealing with white light, what we actually see is all of the colors of the rainbow, or all of the colors in that visible spectrum. This is how a rainbow is produced. The sun shines white light through the raindrops. The raindrops act as a prism, and they separate the light into the rainbow. Now, what we need to talk about is how this light is actually produced. And this is what Bohr was really trying to figure out. Now, how we refer to what is the result of the light passing through the prism, we call it a spectrum. So we call a continuous spectrum one where we have white light, or we have all the colors of the rainbow. So it basically blends from one color to the next, and that's why we call it continuous. Now for hydrogen, we don't see all the colors of the rainbow. We only see these very specific lines. So we call this a line spectrum, or an atomic spectrum. And this is much like a fingerprint. Hydrogen will always produce the same color of purple, and therefore will always result in the same line spectrum. So we can use this to identify unknown elements. Now this little animation here, I encourage you to watch, because it shows you where these different colored lines come from, which we're going to discuss next. So Bohr was studying hydrogen, and he was studying the spectrum, and he was trying to explain how the light was produced in terms of this quantized energy. These are the specific amounts of energy that are being released. This red line, this blue line, this purple line, they are corresponding to very specific amounts of energy, as we saw from Einstein's formula, E is equal to h nu. Now let's look at his postulates. We know the first two postulates. The electron can only exist in certain spherical orbits. We understand that from the current model, Bohr's model, with the different rings around the nucleus. We also understand this concept. As the distance from the nucleus increases, the energy of the electron increases. And these are the new ideas that help us to understand how light is being released. So first of all, when an electron is in its lowest possible energy state, so in that nitrogen, when we had 2 electrons in the first ring and 5 in the second one, we would call that the ground state of nitrogen. All of the electrons are as close as they can be to the nucleus. If we promote those electrons into a higher energy level, we call that the excited state. And that happens by applying energy to an atom. So when we put those hydrogen atoms into a glass discharge tube and we apply electricity, what happens is the electrons in that atom are able to become excited. So in this little diagram here, if we have an electron on the first energy level, in this case, sorry, it's on the second energy level here, if I give energy to this electron, it's going to be able to jump to a higher energy level. In this case, the third ring. So when the electron was down here, right, if it was its lowest energy state, that would be its ground state. But once it's promoted into a higher energy level, this atom is now in its excited state. This is a very high energy state. The atom doesn't want to stay in this excited state. So what will happen is this electron will return to a lower energy level, and as it returns, it needs to release the excess energy. And this excess energy is released as a photon. And as you know, a photon has a certain amount of energy associated with it, which is proportional to the frequency. So when that electron releases energy, it releases it in the form of light. And this is Bohr's fourth postulate. When an electron falls from a higher energy level to a lower energy level, it emits a definite amount of energy equal to the difference in those two energy levels. This diagram here is a good visual. If this red ball falls from this step to this step, it's going to release a very specific amount of energy. If this green ball falls from this one to this one, it's going to release a certain amount of energy. And this staircase model is meant to help you to understand the fact that the amount of energy that's released is very specific. There's no in between. This green ball can't fall to this point here. It can only fall down one step or down both of these steps, but there's no in between. And that's why these amounts of energy are said to be quantized or have specific quantities. Now, this idea that energy is released when an electron falls from a higher energy level to a lower energy level was studied by Rydberg experimentally. And this is the formula that Rydberg derived. It gave the relationship between the wavelength of the light that's emitted and the energy orbits that the electron fell from and to. So these N's, these are representing the energy levels in the atom. This N is said to be the quantum number. And really, it just means that it's the energy level of the atom for our purposes. So if an electron were to fall from the 5th orbit to the 2nd orbit, we would be able to figure out the wavelength of that light. Rydberg used a constant, 109,678 centimeters to the -1. And N1 and N2 are whole numbers because, as per Bohr's model, there are only specific energies that an electron can be in. Now, this formula and this constant were determined experimentally, but Bohr later developed his own equation based on his principles of the model of the atom, and he applied Planck's constant and Planck's information and Einstein's information to that. He used his theory of electronic transitions and his understanding of his model. And really what it came down to is the fact that he had a formula relating the energy and the energy level within an atom. So this formula, E is equal to -b over n squared, is showing the relationship between the energy level within the atom and the actual amount of energy associated with it. This B is a constant, and it's a combined constant that includes such things as the mass of the electron, its charge, and Planck's constant. And this N is an integer called the quantum number, which is really coming from the orbits in Bohr's model. Now, one thing to note about this is that when you look at the energy in an atom, so if we think of N is equal to 1 as being a certain amount of energy, and then N is equal to 2, the distance and therefore the amount of energy difference between energy levels in Bohr's model are not equal. What happens is as N increases, the difference between the amount of energy gets smaller and smaller and smaller. And this comes from the fact that the energy isn't equal to the constants divided by just N, it's the constant divided by N squared. Now what we're going to do is apply this understanding of the energy having a specific value depending on its distance from the nucleus, and we're going to apply it to Bohr's theory where the amount of energy that's released when an electron falls from one level to the next, so if I've got an electron on the 2nd energy level, if it falls back down to the 1st energy level, I can actually find this amount of energy. Because if I know the energy of the 1st level and I know the energy of the 2nd level, if I can find the difference between the two energies, I can calculate the amount of energy. If you want to find the difference, you need to take the amount of energy at the lower level and subtract the amount of energy at the higher level, which is shown here. So the difference in energy, or the amount of energy that's going to be released, is equal to the energy of the electron in its higher orbit minus the energy of the electron in its lower orbit. Now what I'm doing from this step to this step is I'm subbing in that previously looked at formula. We know that Bohr found that the energy of an electron in a certain orbit is equal to negative B over n squared. So the energy of an electron in the higher orbit is equal to negative B over n in the higher orbit squared. And then I'm going to subtract negative B over n, the quantum number of the lower energy level, squared. Now what I'm doing from here to here in terms of rearranging, I'm just trying to clean things up a little bit. So I've done a couple of things. First of all, I took out the common factor of B. Also, we've got minus a minus. So this became a plus. And so that's why I've got 1 over nl squared minus 1 over nh squared. Okay, so this just cleans up this formula a little bit. Now, ultimately, we want to be able to figure out the frequency or the wavelength of this light. So what we're going to do is use our formula of E is equal to hc over lambda, which we derived earlier, and sub it in here. So when I substitute that in, I have hc over lambda is equal to B times 1 over n squared minus 1 over nh squared. In my last step, I'm just combining all of the constants. Hc and B are all constants, so I'm going to move the hc over, dividing it, and I'm left with 1 over lambda is equal to B over hc, 1 over nl squared minus 1 over nh squared. Now this ultimately is one constant that we can use, and so B over hc is actually equal to 109,730. So rather than constantly, every time I want to use this formula, needing to calculate B over hc, I simply can use 109,730. Now, if you look back to the Rydberg equation, it is the exact same relationship. The only difference between the two is the constant. Rydberg determined his constant experimentally to be 109,678, and Bohr derived his constant using the principles of physics, 109,730. The difference between these two values is 0.05%, which is pretty great if you think about how they approached it from two different directions. The fact that they're getting a very similar value is really encouraging. Now, you'll be asked to use both of these equations. The only thing that differs is the constant, and you'll know from reading the question which one you're expected to use. The reality is, if you make a mistake and you use the wrong one, your value will be pretty close to the same as somebody who used the opposite one. Now this diagram here is just showing you the different electronic transitions of hydrogen. You can see that electrons can fall from a variety of different levels and fall back to different levels. So these have been divided into series. We call the Lyman series all of the transitions of the hydrogen electron falling from any level back to the first level. The Bohr series, all the electrons are falling back to the second energy level. The Paschen series to the third, and the bracket series to the fourth energy level. Because these hydrogen atoms are being bombarded with so much energy, they can absorb different quantities of energy, and that is what's going to define the electronic transitions that they undergo. Now, one thing that's unique about the Bohr series, and it's highlighted here, is that all of the transitions that lead to electrons falling back to the second energy level are the ones responsible for what we see in the visible spectrum. So looking back to that hydrogen spectrum, the red light that you saw was the result of a transition from the third to the second energy level. The green light that you saw is from the fourth to the second, right? And the blue and the purple from the fifth and sixth back to the second. These other electronic transitions will still release energy, but the amount of energy that they will release is outside of the visible spectrum, so we won't observe them as light. Okay, if you look back at the electromagnetic spectrum in your note, you can see these ones with larger amounts of energy will have smaller wavelengths, and so they'll be more likely in the ultraviolet, X-ray to gamma ray region. While on the other side, we'll see infrared, okay, down to microwave, probably more likely in the infrared. Now the beauty of the formula that we've seen is that we can actually calculate each of these electronic transitions. And this is what Bohr successfully did, and why his model was supported for so long, was that he was able to predict the color that would be released and what kind of electronic transition gave rise to it. So let's look at an example here. We want to use the Rydberg equation in order to calculate the wavelength in nanometers of the spectral line of hydrogen, for which N2 is equal to 6 and N1 is equal to 3. Would we expect to see light corresponding to the spectral line? So this is what I discussed previously, and being told in the question to use the Rydberg equation. The formula is 1 over lambda is equal to the Rydberg constant, 1 over NL squared minus 1 over NH squared. The Rydberg constant is 109,678 centimeters to the negative 1, which is really like 1 over centimeters. So I'm putting the unit here, but I'm not worried about it in actually doing the calculation. And I've got 1 over, and this is where we need to be careful. Although the energy is the final minus the initial, because of the rearranging that we've done, the first N that we put in this formula is the energy of the lower energy level. So in this case, it's going to be 3. So I take 1 over 3 squared, and I'm going to subtract 1 over 6 squared. Now you'll know whether or not you've done this step correctly based on the actual answer that you get. If you're getting a negative answer, that should be mysterious, because we can't have a negative wavelength ultimately. If you're getting a negative answer, it's because you've probably got these two backwards. Now, in order to plug this into your calculator, I'd recommend that you do this portion first, and then you're going to times the value that you get by 109,678. And that will give you 1 over lambda. The answer that you get is 9,139. Now you don't want to do too much rounding from step to step, so if you can keep the numbers in your calculator, that's ideal. Now I want to know what lambda is, so I need to rearrange this formula for lambda. So what I'm going to do is bring the lambda over here. So 1 is equal to 9139 lambda. And then lambda is equal to 1 over 9139. Okay, so when you have a relationship like this, 1 over lambda is equal to 9139, to solve for whatever's on the bottom, we need to just take the reciprocal of this, or 1 over this value. And the value that I get is 1.09 times 10 to the negative 4. Okay, and this answer, because my Rydberg constant was in centimeters to the negative 1, and then I did 1 over centimeters to the negative 1, I'm left with centimeters. To convert from centimeters to nanometers, what I need to do is divide by 1 times 10 to the negative 7. Okay, and you can do this in 2 steps. You can convert your centimeters to meters, because you know the relationship, and then convert from meters to nanometers, just like we did in the previous example. So when I divide this by 1.09 times 10 to the negative 4 by 1 times 10 to the negative 7, I'm left with 1,090 nanometers. So the question asks us to report the wavelength in nanometers, which is 1,090. And then it asks us, would we be expected to see the light corresponding to this spectral line? As you know, the visible region is from 400 to 700 nanometers. So the answer is no, we would not be able to see this. Okay, and you could put a more complete explanation by saying that it's not within the visible region. At this stage, I'd recommend that you do practice number 2. In this one, it's talking about using the Bohr equation by its reference from the 10th Bohr orbit to the 4th. So you can do that practice question. On the next page of your notes, there are additional practice questions, as well as the key formulas summarized. Now this is our springboard into the new model of the atom, because this calculation that Bohr was doing, as I've made reference to a few times, applies only to hydrogen or one electron systems. He wasn't able to predict the spectral lines in other atoms, and therefore his model needed to be modified. And next class, we're going to look at how the model changed.